So let's do a couple of examples before we end this podcast. My first example here is how much heat is being absorbed when 24.8 grams of water at 100 degrees Celsius at 101.3 kPa, remember that this is the same thing as 1 atm, is being converted to steam at 100 degrees Celsius. So let's draw my heat curve. And my heat curve basically looks like a slanted staircase. Here's my solid, liquid, and gas. This is my liquid and solid. Here, this is my liquid and gas. Or I could actually write solid and liquid, doesn't really matter. And it seems like we are going from 100 degrees Celsius liquid, point A, to 100 degrees Celsius steam. And then if we are in this part of the phase diagram, I know that I'm using the heat of, in this case, vaporization. And heat of vaporization is a positive value because we're adding heat. We're going from left to right. And so this is 40.7 kilojoules for every 1 mole. Let's find out how much water we have. We have 24.8 grams of H2O, and I know that 1 mole of H2O weighs 18.02 grams of H2O, and that comes out to be 1.37 moles of H2O. And so the amount of energy that is required to melt that much water is going to be 1.37 moles. And I know for every 1 mole, it is positive 40.7 kilojoules. So this number times by 1.37 mole is going to get you kilojoules. So in order to so this is my answer here. And so in order to evaporate off 24.8 grams of water at 100 degrees Celsius, then you need to add 55.8 kilojoules. Kilojoules is my kilojoules. To make that happen. Okay. Example 2. How many grams of ice at 0 degrees Celsius will melt if 22.25 kilojoules of heat are added? So let's say that I have a block of ice, and if I add to this ice 2.25 kilojoule, the question is, how much ice would I have left over, and how much water would I have left over, and they will both be at 0 degrees Celsius. Okay? So I know that the formula is Q is equal to the number of moles of water times by the heat of fusion. I know that heat of fusion is positive 6.01 kilojoules per every 1 mole. I know the amount of heat that was added was 2.25 kilojoules. So it becomes 2.25 kilojoules is equal to the number of moles times by the 6.01 kilojoules per mole. And so I am going to just divide out this number, and so the number of moles that would melt, or the moles of ice that would melt, would be 0.374 moles of water. But the question is asking for how many grams of ice, and so I'm going to have to convert that into grams, and so I would have to do my picket fence once again and put 1 mole 18.02 grams, and that comes out to be 6.74 grams of ice that would melt and become 0 degrees Celsius water. So things can actually absorb or release energy while dissolving in water. So this may be a vocabulary that you are familiar with. If not, then please clarify this with me in class. But when I say solute, solvent, and solution, you can kind of think of it as an example of salt water. When you add salt to it, the solute is the salt, the thing that you have less of. The water is the solvent, which is the thing that you have more of. And solution is the mixture of the salt and the water. So heat changes can occur when a solute dissolves in a solvent or when things dissolve in water. Let me come back to this a little bit further once I give you an example of what I'm talking about. So here is an example of sodium hydroxide being put into water. If you can take a look at this beaker, you can see that sodium hydroxide, pellets of sodium hydroxide is just being put into the water. But this releases so much energy that the temperature of the solution may increase very rapidly, and the temperature may rise so fast that the solution will boil and possibly splatter a hot caustic solution. So, in order to prevent any harm to whoever is trying to dissolve sodium hydroxide into water, you have an extra container outside the beaker, and this container has ice in it, ice and water in it, which will absorb all the heat that comes out of this dissolving process and make it a little bit safer. So when I say the heat of solution, I'm talking about the heat or the energy released or absorbed by dissolving 1 mole of the substance. So please remember that if you have a delta H of solution, which is a positive delta H of solution, then this is absorbing heat, which is the same thing as an endothermic process. Okay, versus if it is a negative delta heat of solution, this is releasing heat. When you add this stuff, it's releasing so much heat that this is an exothermic process. And for sodium hydroxide, this is an example of an exothermic molar heat of solution. So if I tell you that sodium hydroxide, solid pellets, is put into H2O, and you have a separation of the Na from the OH, and you have NAs in, and this AQ means aqueous, meaning in water, or aqueous, like the Spanish word agua. Agua means water, so aqueous means in water. You have Na and the OH that split and gives you a heat of solution of negative 445.1 kilojoules per 1 mole. So that's how much energy it releases for every 1 mole. The heat is released as the ions separate by dissolving and interacting with the water, and thus becomes so hot that it actually steams up. So here's an example straight out of your book. It says how much heat is released when 2.500 moles of NaOH is dissolved in water. So we first want to find out how many. No, we don't want to find out how many moles. So we take that heat of solution, and the heat of solution is this right here. And we are just going to multiply the heat of solution times by the number of moles of NaOH you have, and you have this much energy that is being released. And that concludes our podcast for podcast number 2 of Unit 3, and this is our last, or 2 of 2, podcast of Unit 3, and I am done with the content. If you have any questions regarding this, please ask me during class.